focusing on a specific Sn1 reaction, and the reaction we were focusing on is this reaction right here. This iodoethane. And this is iodo because of the iodine, ethane. And in the previous video we named this one AB. And of course you know eth means two carbons, so that's A and B, 1 and 2. Ane means alkane, all single bonds. There's no double bonds in this molecule, it's all single bonds. We said that we wanted to associate this molecule with the iodoethane. This hydroxide. It's a specific reason why we're going to use hydroxide with our iodoethane. And we're going to put it at 25 degrees Celsius. We're going to talk. We never talked about that. And specifically in this video, we're going to talk about the potential energy diagram related to this Sn2 reaction. But specifically right now, we want to focus on these reaction conditions. Let's talk about some things we didn't talk about in the previous video that I said that we were going to talk about. Okay, so this is at 25 degrees Celsius, and also we're going to put it in acetone. I didn't talk about why I wanted to submerge the hydroxide and the iodoethane in acetone. And of course, our product that we got in the last video is ethanol, or drinking alcohol. So this, and we got O, we got ourselves H, 2 lone pairs. Okay, and this is ethanol. So let's explain first some of these conditions that favor a certain reaction. Let's start off with some of the simple ones. Okay, so this 25 degrees Celsius here, all substitution reactions are favored at 25 degrees Celsius. When I say what I mean is by the what I mean by all substitution reactions, I mean Sn1 reactions. We're gonna talk about that, and we're gonna talk about Sn1 just like we talking about Sn2, and Sn2 videos. What Sn2 reactions? The focus of this video, these series of videos, is favored at 25 degrees Celsius. All substitution reactions are favored at 25 degrees Celsius, and this is like a thermodynamic type of thing, you know, related to the potential energy diagram, the focus of this video. Potential energy and all that stuff, you know, energetically, thermodynamically, it's Sn2 reactions like 25 degrees Celsius. You know, this is what they prefer. Their mechanism is associated with this this temperature, and this temperature is associated with a certain energy, I guess you can say. So you can really favor Sn2 the substitution reactions by keeping it at 25 degrees Celsius. Usually when you get higher than 25 degrees Celsius, closer to like 55 degrees Celsius, you'll see in some books 50 degrees Celsius. Some books will even go to 100 degrees Celsius. But when you get these higher temperatures, these favor elimination reactions. And these reactions create multiple bonds, like double bonds and triple bonds and things like this. But we're not trying to create more bonds. All we're trying to do in substitution reactions, like that's what the S means in Sn1 and Sn2. We're just trying to, just like in a basketball game. Think of A and B as the basketball game, and think of I as one of the basketball players. Think of him as playing bad. So the coach turns him into like in the mechanism previously we talked about, the coach is going to turn him into a leaving group, and he's going to have to leave the game. A and B are the game. He'll leave in the mechanism, in the Sn2 mechanism, and this guy, the hydroxide, the nucleophile, he's LeBron James or somebody. He's going to come into the game, and then this player is going to leave as a leaving group. So now LeBron James is in the game, or in the molecule, or whatever. So this is a good way of looking at it, or seeing the substitution. One player subs out, one player subs in. This is substitution. Leaving group leaves, nucleophile takes electrophile, or the player gets into the game. So sub out, sub in, substitution. Now Now, the most well, let's get some terminology out of the way. Okay, so every Sn2 reaction is going to have a nucleophile. And I'm going to do some videos on nucleophiles if anybody requests them. And, you know, this nucleophilicity is a difficult thing to understand for you. I can put up a separate video because it'll take a lot of time to explain that. And we're trying to focus on the Sn2 mechanism. I mean, the Sn2 reaction and everything related to it. Now, let's talk about the electrophile. Let's see why that carbon right there is the electrophile, why it's interesting. And of course, like we said previously, in every organic chemistry reaction, the nucleophile always attacks the electrophile. And this is the underlining grand concept of all organic chemistry reactions that we need to understand here. And if you understand this, you understand everything. Okay, back to the molecule, the iodoethane. Now, A is going to be the most electrophilic carbon, so it gets attacked by the nucleophilic atom, oxygen, with its orange lone pair. Now, okay, the electronegativity goes to iodine, like this. It goes directly to iodine, like that, because iodine is a halogen and it's more electronegative than carbon A. So the electronegativity goes this way. So it makes this bond a bit polar. It's a polar bond, so that's partially negative, the iodine. And the A, why it has the ability to act as the electrophile is because it has a partial positive charge associated with it. You know, and this is how it's able to take on being an electrophile. So in this reaction, the Sn2 reaction, the I is considered to be, you'll see them call it the leaving group. The leaving group. Okay, let's see. Okay, the whole thing. You'll see your professor refer to the whole thing as the substrate. Hopefully I spelled that right. Substrate. Okay, and of course we said this was a nucleophile. That's a symbol for nucleophile. That's the electrophilic carbon. Okay, of course this is the product. This ethanol is the product. Now let's talk about the most interesting thing in the Sn2 reaction, the conditions. In my opinion, I found this thing to be the most interesting because we got the minor stuff out of the way. This is like this is just the minor stuff, but this is the interesting stuff. Usually in organic chemistry, something interests me, and I like this idea right here because it even makes you have a deeper understanding of the rate law, how it relates to the mechanism. Let's take a look at why did I put everything when I did this reaction in my beaker in the lab. Why did I put everything in acetone? It's because that's all I had in the lab on hand. I didn't have anything else, and I specifically picked this because this is all I had. But I know that that's going to favor me to form ethanol better, faster, and just help me get a better yield of ethanol, or help me, you know, make more of it, or you know, get a better use of this. Mixing these two together, I can get more of this stuff if I mix it just one time. Why do I put it in acetone? Well, it's going to take an explanation to understand that. I'll finish this problem in the next video.